In this exercise we wish to find the region, or disk, defined by the locus of the complex numbers, z, satisfying the formula, magnitude of z, minus 2. Minus 2I, less than or equal to square root of 2. And based on the result, to give an answer to 4 distinct questions. Now by setting x, the real part, y, the imaginary part, of the complex number, z, and by substituting in the given formula, we get that the locus of z, is a closed disk, in the complex plane with center the point k with coordinates 2, 2 and radius square root of 2. That is the circumference with the interior of the circle. So the given formula I represents a closed disk, boundary plus interior, in the complex plane. More detailed. For every complex number on the circumference we have magnitude of z minus w equals to square root of 2. But for every complex number into the interior of the disk we have magnitude of z minus w less than square root of 2. Given a circle and an external point, we know from the Euclidean geometry that in order to find the points of the circle of maximum or minimum distance from the given point, we use the line that connects the point with the center of the circle. So now in order to find the complex number of the above locus with the maximum or minimum magnitude, we draw the line that connects the origin with the center, k, of the circle. In our case this line is OK, with equation y equal to x. We now find the intersection points of the circle with the line, by solving their system of equations. And we get that the point, c, of the circumference of the circle, with coordinates, 1, 1, is the closest to the origin and point, d, with coordinates, 3, 3, is the furthest from this. So point, c, of the circumference of the disk, with coordinates, 1, 1, that has the minimum distance from the origin, corresponds to the complex number z, min, which is equal to 1 plus 1, I. On the other hand point, d, of the circumference of the disk, with coordinates, 3, 3, that has the maximum distance from the origin, corresponds to the complex number z, max, which is equal to 3, plus 3, I. So from all complex numbers of the above locus, z, min, has the minimum magnitude. And z, max, has the maximum magnitude. From Euclidean geometry we know that from a point external as to a circle, we can draw 2 tangent lines to the circle. These 2 tangents are equal in length, and symmetric as to the line that connects the point with the center of the circle. So now, we can draw 2 tangent lines, from the origin to the circle C. It is more than obvious that points A and B, which are the points of tangency, correspond to the complex numbers of the locus with maximum and minimum argument respectively. Now our goal is to determine the coordinates, x, 0, and y, 0, of point A. This can be done by a couple of standard ways. Let us call the first way the trigonometric method. Since the coordinates of points O and K are known, we can calculate the length of OK segment. Triangle OAK is a right triangle at vertex A. Also segment KA is half of the segment OK. So in the right triangle OAK, one of the right legs is half of the hypotenuse, in this case the angle opposite to that leg, that is angle AOK, is pi 6 radians. So now we conclude that line OA forms an angle of 5 pi 12 radians with the positive x-axis. The next obvious step is to calculate the slope of line OA, which is equal to 2 plus square root of 3. So the equation of line OA is y equals to the quantity 2 plus square root of 3 close quantity times of x. Now in order to find the coordinates of point A, we solve the system of equations of tangent line OA and the circle. The coordinates of point A are shown at the end of the page. Also, since points A and B are symmetric as to the line y equal to x, we can also get the coordinates of point B. In this page we can see the complex number, z1, of the locus with the maximum argument. The maximum argument is 5 pi 12ths. And here we have the complex number, z2, of the locus with the minimum argument. The minimum argument is pi 12ths. In this page there is an additional question. Of course one could ask, what if vertex, O, was not of pi 6th radians? Which is a rather convenient outcome. Let's say that O is any point on the complex plane, external as to the circle, and we know the coordinates of points, O, and, K, and the radius, R. We can still use the lengths of segments, K, A, and O, K, labeled, R and D, respectively. From these we can find the arc, sine, and the arc, cosine, of vertex, O. And subsequently obtain the coordinates of tangent point, A. Another more general way to determine points, A, and, B, is to use a geometric construction. In this method, shown in this page, the points of tangency, A, B, are obtained, as the intersection points of the two circles in the geometric construction.